I'll give it like a week and I'll go back.
All right, let's get started then. So we have a graph here, represents the velocity, which is measured in meters per second of a particle that is moving along the x-axis. So again, remember this graph here is representing velocity. At what values of t does the particle have no acceleration on the interval from 0 to 10? Justify your answer. So we want some x values where the acceleration... Still frozen? There we go. Thank you. We want some x values where the acceleration, or where there is no acceleration. So remember, that's a velocity function. Think about the relationship between velocity and acceleration, how you get from one to the other. Visually with the graph, what are we going to try to look for? Daniel?
Areas where velocity does not change.
Okay, possibly. What do you mean by that?
Like where the slope is 0. Or horizontal points, right?
Okay, let's see. Well, not exactly. So we're saying no acceleration. They're not saying an acceleration of necessarily 0. They're saying there's no acceleration. You can't even find an acceleration value.
Oh, I see.
Stevie?
Zero.
What do you mean by that?
Whenever the velocity is equal to 0?
No. There still can be acceleration when velocity is 0. Allison?
Maxes and mins.
Possibly. What has to be true about those maxes and mins? You're really close.
Like the derivative, which is acceleration, has to equal 0.
Okay, she's almost there.
In order to find no acceleration, there cannot be a value, so it has to be undefined. So at the maxes and mins that are not differentiable.
Yes, not differentiable. So the maxes and mins that Allison was mentioning, but they have to be non-differentiable points, so sharp points. So what values do we have no acceleration? Go ahead, Dan.
1 and 8.
1 and 8. Okay, so those are two of the values. There are more than that, though. Allison?
0 and 10.
We're not going to count the endpoints because we don't know necessarily. It's starting at 0. We have to start somehow, so there's going to be acceleration there. But at the 10, we don't know if we continue on past that. Right now, we're just looking at that interval. But I like your thought process. Go ahead.
1, 3, 6, and 8.
Yeah, so if you look here, 3 and 6, these are going to be your other parts where they're not differentiable. And Allison, if you look at our interval, we have the open interval here. We're not including those points, so that's another reason why. But your thought process was correct in thinking why those would be there. Okay, so those are the points. We're going to say because the graph of v of t has sharp points. So that's our explanation. Those are the points where there is no acceleration because the graph has sharp points. And if you want to write a note here to yourself, the no acceleration, that means a of t, your acceleration, is undefined. We described that, but we didn't actually write it down anywhere. Again, that's a non-differentiable point. Somebody get the door, please. Before we move on to the next question, I also do want to write this down just as a reference. So if you pick any point on this current graph, that specific point is going to tell you what? If you just pick a point, that's giving you what? Go ahead.
Velocity.
A velocity. Thank you. So any points or points on the graph give you a velocity. Points equal velocity according to this graph. If you take the slope of this graph, what do you get? Acceleration. So that's just some stuff that you can, when you get a problem like this, write down at the beginning. That way you have that information so you're ready for any question they ask. So now let's take a look at the, well, I guess part B, but they don't have it labeled. Express the acceleration a of t as a piecewise defined function on the interval 0 to 10. So we know the acceleration is going to be changing. That's why it's going to be piecewise. We have to deal with intervals. So on each specific interval, we need to label what the acceleration would be. So a of t is going to be equal to, and we're going to have some big piecewise function. What would be the first acceleration or the first interval that we're going to look at for an acceleration? Dan?
Probably 0, 1.
Okay, from 0 to 1. So I'm going to put this over on the far side. Our interval is going to be t from 0 to 1. Now what would that acceleration actually be from 0 to 1?
3.
3. You can think of rise over run, however you want to think about that to find it, but the slope would be 3 on that interval. Now we need to find each interval. What would be the next interval?
No. 1.
1 to 3 is the next interval. And I think you already gave the answer, Braden. What'd you say? Yeah, -3 on that interval. Next interval we see goes from 3 to 6. And what is the slope from 3 to 6? 0. Then we go from 6 to 8. And on that interval, what's the slope from 6 to 8? 3. And the last one, I'm not going to be able to squeeze it in at the bottom. I'm going to write it on the other side. We go from 8 to 10. And what would the slope be from 8 to 10? -3 halves. Yep. So if you can squeeze it in at the bottom, that would be better, but -3 over 2 from 8 to 10. And that's all they're really asking. We have gone over the entire interval from 0 to 10, and we wrote down an acceleration for each interval within that interval. Any questions on first or second part? Anastasia, getting caught up, do you have any questions, or are you where we're at yet?
Yeah.
Okay. Okay. On the third part, for what values of t is the particle moving to the right? Same question for to the left, and justify your answer. So we want to know, when is this particle moving right? When is it moving left? When is it moving right? Try to use your graph to help you determine that. Dan?
It was moving right on 0, 2 and 7, 10.
How do you know that?
Because the velocity is positive.
Exactly. 0, 2 and 7, 10. And your explanation is, looking at your graph from 0 to 2 and 7 to 10, your velocity is positive. If your velocity is positive, you're moving to the right. So because v of t is positive. And then moving to the left, what's the interval for moving to the left? Go ahead.
2, 7.
2, 7. Because v of t is negative.
Yep.
And we could tell all of that just from looking at the velocity graph up above. All good so far? All right, lastly, find the average acceleration of the particle on the interval 1 to 8. Show your work. Again, think of that. We've done problems like this in the past few sections. They're asking for average acceleration. How do we find average acceleration?
you take the two intervals and like v of b minus v of a over b minus a.
Exactly. So the average acceleration is equal to the slope of velocity So just writing down some notation so we can understand that if we look back, the average acceleration is equal to the slope of the velocity. And the interval we're specifically dealing with is 1 to 8. So v of 8 minus v of 1 over 8 minus 1. What is v of 8? Three. What is v of 1? 3. We get 0 over 7, which is just 0. 0 what? What's our units? Yeah, meters per second squared. So we're saying over that entire interval, if you average out your accelerations, your average acceleration over the entire time is 0 meters per second squared. With your speeding up and slowing down, your accelerations average out. All right, if we're all good with that, we'll go to the back. At the top, we're going to create a few definitions here. So, they want to know the definition of net distance. This is going to be the distance between the point of origin and the final position. The distance between the point of origin and the final position. This is also known as displacement. Displacement. The distance between the point of origin and final position, also known as displacement. So that's what we kind of talked about with the acceleration, kind of that way. We found from the origin to the final position. But we would need to do that with the velocity, or the distance, not the acceleration. Now we want to find the definition of total distance. This is going to be the sum of all distances moved in any direction. The sum of all directions, or all distances, sorry. The sum of all distances moved in any direction. Sum of all distances moved in any direction. So now, after writing those two definitions, think about the next question. If a particle is moving in the same direction the entire amount of time, what can be said about the net distance and the total distance? If they're moving in the same direction the entire time, what would be true about the net distance and the total distance? Yes, they would be equal to each other, exactly. The net distance equal to total distance. Exactly. So another way to think of that, we've done problems like this before, but if somebody walks 5 feet to the right and stops, and then walks 5 feet more, their net distance was 10, they've went 10 feet. Their total distance was also 10 feet. But if you think about somebody walking 5 feet to the right, stopping, and then walking 5 feet to the left, their net distance is what? 0. They started where they stopped. Their net distance hasn't changed. Their total distance, though, they did move. They went 5 and then 5, so their total distance was 10. That's what you need to think about with the net and the total distance, how they're different. All right, to find the net distance, other words known as displacement, a particle travels in an interval. So, on an interval, AB, so the closed interval AB, the net distance is it's going to be the absolute value P of B minus P of A, where P of B, that's the end position, and P of A is the start position. So end and start. So that's to find the net distance. You just take the value of your end distance and the value where you started and subtract them and take the absolute value. That's your net distance. And again, this is P, so this is a position function. This is your end position and your starting position. To find the total distance a particle travels on an interval. So again, we're dealing with that interval A to B. I'm not going to write this one up as formally. We're dealing with that interval A to B. Particle does not change direction, so particle does not change direction. The total distance would be equal to the absolute value of P of B minus P of A. So again, that's what we'd mentioned up above. That's going to be the same as the net distance. So if you're moving to the right the entire time, your net distance is going to be the same as your total distance. That's why these two are the same, but that's only if you're traveling in the same direction. So the particle does not change direction. This is the total distance. But if direction changes, for some time equal to c, whatever that c value is where the time changes, on your interval A to B, total distance is now equal to the absolute value, P of B, minus P of C, that value where it changed direction, so the absolute value of that, plus the absolute value of P of C minus P of A. So again, this is because at some point C you change direction, so you have to find the distances of both pieces and then add them together. If you change directions more than once, you're going to have more pieces that you have to add together. So anytime you change a direction, you're going to have to add a piece to this and add your pieces together to get your total distance. Again, if you don't change direction, it's easy. It's the same as net distance. It's when you change direction that gets a little tricky. You have to add all your pieces together. Which part, Braden?
Is that plus in the middle? Yeah.
Yeah, P of B minus P of C, this is absolute value, plus P of C minus P of A. And they're both absolute values. Because you're taking whatever that distance is and adding those distances together. All good now? Alright, let's take a look at the bottom example then. The position of a particle is given by the function P of t listed there, where P of t is measured in centimeters. Find the net and total distance the particle travels from time 1.5 seconds to time 4 seconds. So that's the interval we're dealing with. Let's first deal with net distance. That's the easier one. So net distance. Net distance. We take the formula from up above that we just found for net distance. P of 4, your end position, minus P of 1.5, your starting position. Go ahead, get a calculator. You need to find both values subtract them and take the absolute value, that's going to be your net distance. So go ahead and calculate that. I'll wait a minute or so while you do that. When you find a value, let me know what you get. This is the net distance. Braden?
58.75 centimeters.
58.75 centimeters. Again, that's a distance that was traveled. That's the net distance. So your net distance was 58.75. Now they also want total distance. So we have to determine, did we change directions at all? And then if we did change directions, we have to add all those little pieces together. So if we're given a position function, how do you think we can determine if we've changed directions at all? If we were moving right and then went left, or if we were going left and then right, how can we determine, given a position function, what happened?
You need to find the derivative to give you the velocity function. Then you need to find out when that derivative, if ever, equals 0 or negative.
Yeah, the critical point. So we're going to take the derivative to find a critical point, kind of like those tables we made before. We took the derivative, we found the critical points, and we found when's it positive, when's it negative. Then we know it's increasing or decreasing. So that's what we need to do. We need to find v of t, the derivative. So the derivative of this function up here is not too bad. 6t squared minus 12t plus 8. That's the derivative. We need to set the derivative equal to 0 to find critical points. I can factor out a 2 from everything. So factor out a 2. I get 3t squared minus 6t plus 4. Do you think we're going to be able to factor that? I don't think so. So if we can't factor, what do we have to do? It's been a little while since we've done it, but... Yeah, Stevie, you got it. Quadratic formula. So we're going to have t equal to, does anybody remember? We're going to have the opposite of b, so we have 6 plus or minus, very good, square root of, so 36 minus 4ac, so 4 times 3 times 4, all over 2a, which is 2 times 3, so I'm just going to simplify that to 6 right away. So simplify underneath the radical first. We get 6 plus or minus square root of what value over 6? If you need me to reread any of this, just let me know. But you get negative 12 under the radical. Before we solve any further, what does this answer tell you?
That you're going to get imaginary numbers, so there is no critical point.
Okay, so we know any points here are imaginary numbers. So v of t does not equal 0. So on the interval, let's just write a small table. The interval we're dealing with is 1.5 to 4. That's the only interval we're going to have in our table. The velocity is what within that interval? We need to determine at this point in the problem, does it matter if the velocity is positive or negative? You found out it's what, Braden? I heard. Okay, you found out it's positive. Does it matter to us at this point if it's positive or negative? See some head shakes out there.
No.
See some uncertainty. So really, it doesn't matter if it's positive the whole time or negative the whole time. The only thing that matters is that it's what the whole time?
The same.
Going the same direction the whole time. So at this point, we don't care in terms of this problem whether it's negative the whole time or positive the whole time. We just care that it's staying the same. Since it is the same the whole time, what do we know about the total distance? It's the same. So as your concluding statement, you can say, since v of t is always positive on 1.5 to 4, particle is always moving to the right, so the distances are the same. V of t is positive on 1.5 to 4, so always moving right. So the distances are the same. V of t is positive on the interval 1.5 to 4, so always moving right, so the distances are the same. We don't have to do any other calculations for the total distance. Lucky us, we don't have to add all those pieces together. Let's go ahead to the next page once you're done. Anybody still copying? I don't want to move it if you're not done. All right, on the next page. So what I'd like you to do is I'd like you to get a little bit of practice without just copying down. So we have two problems here. Let's just focus on the first one first. So that top one. They're going to ask about net and total distance again. So they give you an interval, they give you a function. I'd like you to go through the steps we just went through with that previous problem. Find your net distance. Then use your position function to try to find if your distances change at all, and see if you can come up with and use the definitions we've created today to find your two answers. So go ahead and work on just the first one. If you want to work with a partner, or if you're sitting in a group, I don't care. You can work together if you want to turn around and work with somebody, but take some time, work on this one together, see if you can figure out what the answers are. Anybody find any net distances yet? You guys find your net distance yet? I know some people are further than others. I just want to know, have you guys determined, does it change direction? Yeah, you should. If you haven't got to that part yet, once you get there, you should find out that it does change direction. So I know we haven't explicitly done an example like this, but if you can get to that part, we'll go over how to find the answer if you're not sure. If you want to give it a try using the definitions we created today, you can do that too. But okay, so far I put a little bit of the answer up there. The net distance, you should have been able to get this here. Then you go through the steps like we did on the front side. Velocity, setting it equal to 0 because you had to take the derivative. So if you got stuck on the derivative there, if you have e to something, how do you get rid of that? Well, you take the natural log of both sides. So if that's something that you forgot, try to remember that, but there's a little reminder there. And that should be your table where you find out that it changes direction. Are there any questions up to this point? This is half the question. So we looked at that interval, found a critical point. That critical point was within the interval from 0.5 to 1.5. So we had to test both. We found that over here it was negative, over here it was positive. So it did change directions in the interval. So now that I know it changes directions, how do I actually find the answer? How do I find the total distance? I do know that it changes direction. I have the intervals here. How do I find the total distance now? If you're not sure, look back at your definition we created today. How many pieces do we need to add together? 2 pieces. Has anybody found a final answer yet for total distance? I'd like you to try to find it before I show you what the answer is. At least give it a try. Use that formula we created in the definition today. Again, when direction changes, that doesn't mean that the net and total are going to be the same. Okay?
If direction does change, could they still be the same or should they not?
They shouldn't be. Because if you've changed direction, no matter if you go 5 feet, Daniel, and then come back 2 feet,
Yeah.
your net and total are different. No matter how you do it, they're going to be different.
I don't know what I'm doing wrong then.
Well, let's take a look at this answer then. So we know the particle changes direction at this point here. That was our critical point. That's within the interval. So this is already what I've explained right here. We found the critical point. It's within the interval. So the net and total distances are not the same. This is what we explained from here. And this is the actual calculation on how you find the total distance. Remember, we have 2 pieces now. We have the 1.5 to this point, critical point, the absolute value of that, plus from that critical point to our starting point. These are the 2 absolute values we have to add together to get our final answer.
Let's see what I did wrong.
Any concerns, questions, confusions? If you want me to look at your paper individually, I can do that too. If you weren't sure before, does it make better sense now seeing how that answer is put together? How the definition was used? That we actually have these 2 pieces added together? because we have two pieces here and it changed direction. Now, what if this here, if you're looking up here, if this critical point, if we found these were both positive or both negative, would that change this answer? If this problem just happened to be both positive here or both negative, would we have had to have done two pieces if the problem ended up as both positive or both negative?
No, because what PC would be 0, so it wouldn't do anything.
Exactly. So they would just be going the same direction here still if they were both positive or both negative. There was no change. So you could have just done the same thing as net distance if the problem would have been the same here. But we notice they're different. It did change direction. Just something to be aware of if you see it. So what I'd like you to do, the question down below on the bottom of the page. We have a little bit of time left. I would like you to just start working on that one. You have a few minutes left. Work on it. Get as far as you can. Work with somebody. We're going to review the answer for that tomorrow at the beginning of class. So try to get as far as you can with it today, and tomorrow we will start with that problem, reviewing it.